Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to the course Analysis of Variance and Design of Experiments. So, in this lecture we are going to talk about the two-way analysis of variance, but when we are trying to consider the interaction between two factors. Now, before I move forward, it is very important for me to inform you that in the last lecture we had done the topic on two-way analysis of variance when there was no interaction, and for that we had done the topic on say one-way analysis of variance. In one-way analysis of variance I had given you all the steps that how are we going to obtain minor steps, different expressions, and I tried my best to explain you that how we are going to obtain them and how are they going to be used, and they are based on which concepts. And then in the case of two-way analysis of variance without interactions, I implemented those things. I had given you some algebra, some proofs, and rest of the things I had extended from one way to two way. Now, in this lecture, when we are trying to consider the two-way analysis of variance with interactions, we are going to use the theories, result, formulas, derivations, whatever we have done in the last two lectures. And in this case, in case if I start doing all the proofs, this analysis will become quite long, and the proofs are not difficult. They are very simple, very straightforward, exactly on the same approach, same methodology what you have done in the case of one way and two way. So, it is very important for you that you should know the one way and two way analysis of variance very clearly. You should know how are those steps being obtained, what type of theories, what type of fundamentals they have been used, and then using those things we are simply going to employ them here, and without doing much algebra you should be able to obtain those steps without any problem. And in case if you have understood those two lectures on one way and two way, I assure you there will not be any problem, but if you have not, then this lecture will become little bit troublesome. Troublesome in the sense that you will have to spend more time and you have to understand it. So, let us begin our lecture, but if you have not revised it, I will request you that you first revise and then you begin this lecture. Right. So, now if you try to see, we had considered earlier the two-way analysis of variance model, where we had considered two subscript I and j to indicate the observations which are based on two factors A and B. And we had considered that there is only one observation in a cell. So, there cannot be any interaction, and so we had developed the model for the interaction effect, but since there was only one observation in every cell, in every plot, so we had substituted the interaction effect to be 0 and we had analyzed the model y I j is equal to mu plus alpha I plus beta j plus epsilon I j. But now when you are trying to consider the interaction effect between the two factors, then obviously you need to have more than one observations in a cell, right. Yeah, there can be two options, that whether you have got the same number of observation in every cell, or you have got different number of observation in every cell, right. When I am trying to say the cell is something like plot, or the same setup in which you are going to obtain more than one observations, right. So, obviously, when you are trying to consider the interaction effect between the two factors, you need to have three subscript I, j and k. Why? I and j, they are going to indicate the observations due to factors, say factor A and factor B, and k is going to indicate a particular observations which have been obtained after giving the treatment effects controlled by factors A and B. And remember one thing here, when we are going to conduct the experiment, then we are going to control only the factors A and B. We are simply trying to choose different levels, combination of the factors A and B. For example, if factor A is quantity of fertilizer and factor B is this irrigation level. So, suppose if I say I am taking 2 kilogram of fertilizer and 30 centimeter of irrigation, then we are just going to repeat this experiment again and again. So, the values are going to be assigned only to the true two levels of the treatments of factor A and B, and the interaction effect is going to be estimated from the same set of observations. And one thing you can observe in this analysis of variance, which is very important, which you have now understood, but possibly you have not observed it, that you have got only here the observations on y's, that means a response variable, and you are trying to estimate the effect of different factors as well as now interaction effect also using only those observations. So, sometimes you are trying to take their average within group, sometime in the entire population, you are trying to take different type of elementary contrast in terms of their means, etc. So, that is a very important or say very say peculiar characteristic of this analysis of variance, right. So, now let us try to consider this y I j k to indicate the kth observation in the I jth cell. So, this means the observation in that particular cell, this is receiving the ith level of factor A and jth level of factor B. Right, my symbols and quotation, they are going to be the same what we have used in the case of two-way analysis of variance. So, we are assuming that the two factors A and B, they have got I and j level. So, I small I is going from 1 to capital I and j is going from 1 to capital J, and now we are trying to take suppose different observations in a cell. So, we are going to indicate here a small k which has a range from 1 to capital K. And this y I j k, they are independently drawn from the normal population with mean mu I j and variance sigma I square. One thing I would like to clarify here, that here I am trying to take the mean here as a mu I j k, and it is not mu I j k. Remember one thing, sometimes people get confused with this thing. So, because here if you try to see, there are only two factors A and B on which you are trying to take the observation. So, that is why you need to have only here mu I j. Well, in case if you are going for three-way classification, then obviously we will try to consider here mu I j k. That is the point where we have to be very clear. Right. So, okay. So, now I can express my observation y I j k here as a mu I j plus epsilon I j k, where epsilon I j k are the IID random errors which are identically and independently distributed, and they are following normal 0 sigma square distribution. So, as you know that during the estimation part we will not require the assumption of the normality, but when we are going to conduct the test of hypothesis, then in order to find out the derivation of the statistics, we will require the normality assumption. Now, you see, we are going to follow the same steps for the development of analysis of variance what we have learnt in one way and two way analysis of variance. The only thing is this, now we have to adjust it in a proper way. We have to make certain assumptions, and then we have to simply employ the least square principle or say maximum likelihood principle, but we will prefer here to employ the least square principle, because we already have done such an algebra in the case of one way and two way, and my objective is that I would try to follow the same steps or the same approach for the algebra in this two way classification also, so that there is no confusion in understanding it. So, right. So, the first step is this, we have to reparameterize the model. Now, you know why we are trying to do it, because unless and until you try to express these treatment effects or these factors effect in the form of a contrast, you cannot estimate them, right. Now, you know the entire theory, so I do not need to explain you again and again, right. So, in case if I try to write down here expected value of y I j k, this is going to be mu I j, and this part is going to be now be the same what you have done in the case of two way analysis of variance. That is exactly the same thing. So, what are we trying to do here? We are trying to add and subtract here mu I naught, we are trying to add and subtract here mu naught j, and we are trying to add and subtract here mu double naught, right. And my objective is this, I want to write this model in terms of the factors say A, B and their interactions. So, now we can write it down here as say mu double naught plus mu I naught minus mu double naught plus mu naught j minus mu double naught plus mu I j minus mu I naught minus mu naught j plus mu double naught. And these things I can write down in terms of the symbols alpha I, beta j and gamma I j. So, now you can see here this mu double naught we are trying to indicate by here mu, this is here like this. This mu I naught minus mu double naught, this is here alpha I, this is like this, and similarly here mu naught j minus mu double naught, this is your here beta j like this, and gamma I j, which is the interaction effect, that is going to be written as here say mu I j minus mu I naught minus mu naught j plus mu double naught. And you can see here that we will need here the constraints also, so that there is no problem in the estimation of this linear parametric function at a later stage. So, we assume here now that summation I goes from 1 to capital I, alpha I is equal to 0, summation j goes from 1 to capital J, beta j is equal to 0, summation over I gamma I j is equal to 0, and summation over j gamma I j is equal to 0. So, you can see here we, for this gamma I j we are trying to put here two constraints based on the sums of sum over I and j both, right. And we assume that the design matrix X is of full rank, so that all the parametric functions of mu I j they are going to be estimable, right. Okay, so, now we have defined our model. Now, if you try to see, if you have not understood the theory what we have discussed in the case of one way analysis of variance, that how we have obtained this model, why such constraints are there, it will be difficult for you to understand this lecture with basic fundamentals. So, now I assume that you have understood those things. So, you can very easily follow that we are following the same concepts here also. Now, the second step is this, we have to state the hypothesis that we want to test. So, now obviously, we have here three parameters or three types of effects, one related to alpha, another related to beta and another related to interaction effect gamma. So, based on that, in one way classification we had only one set of null and alternative hypothesis. In two way classification we had two such a hypothesis. Now, you are trying to have here two-way plus interaction effect. So, we are going to have here three sets of such hypotheses. First hypothesis is about alpha, that H naught alpha is that alpha 1 equal to alpha 2 equal to alpha I, they are equal to 0, with alternative that at least one pair of alpha I and alpha j, they are not the equal. Similarly, other set of hypothesis is about beta, that H naught beta, that beta 1 equal to beta 2 equal to beta j is equal to 0, with alternative that at least one pair of beta I and beta j, they are different. And then we have another set of hypotheses here, that all gamma ij's are equal to 0 for all I and j, with an alternative that at least one gamma ij is not equal to gamma ik for j not equal to k, right. You can see here. Now, so you have defined or you have stated here the hypothesis that you want to test. Now, after this, what you have to do? In case if you recall from your one-way and two-way analysis of variance setup, the first step we have to take in order to estimate the parameters is that we have to consider the entire model, and we need to find out the estimators of alpha I, beta j and gamma ij. So, for that what are we going to do? We are simply going to write down here the sum of squares due to random errors. So, you can see here this is going to be here triple summation over I j and k epsilon square I j k, right. And this is being indicated by here E, and if you try to replace here epsilon I j k by y I j k minus mu minus alpha I minus beta j minus gamma I j. So, this gives you here sum of say sum of squares, and you have to simply differentiate it with respect to the parameters mu alpha I beta j and gamma I j, put it equal to 0 and then solve it. Yes, after that, because you are trying to use here the principle of maxima minima. So, since we already have done in the beginning that the second order derivatives are going to indicate that you are really minimizing the array sum of square at those estimates. So, I am not doing it here again and again, but that would be clear in your mind that we had done it in the beginning. So, I am not repeating it again and again. Okay, so now if you try to partially differentiate this E with respect to here mu, put it equal to 0, then differentiate E with respect to alpha I, beta j and gamma I j, put them equal to 0, and these equations are going to give you the normal equations, right. Now, what you have to do? You simply have to differentiate them and you have to solve them. So, now if you try to see, you have done the same exercise in the case of one-way classification as well as in two-way classification, and this was a very simple exercise that you simply have to differentiate it and you have to use the constraints like summation alpha equal to 0, summation beta j is equal to 0, summation over I gamma I j is equal to 0 and summation over j gamma I j is equal to 0, and you can obtain the estimates of mu alpha I, beta j and gamma I j without any problem, right. So, now do you think that should I use at least 20 minutes in doing the same thing? Certainly not. So, I will say request you that you try to differentiate it, put them equal to 0 and try to solve it exactly in the same way as we have done in the case of one-way and two-way analysis of variance. And once you do it, then you can obtain here the estimate of mu here as say mu hat is equal to y bar triple 0 or say triple naught. So, why now there are 3 knots? Because you are trying to take the sum of all the observation over I, j and k, and you are trying to divide it by the total number of observation which are I into j into k. So, that is why this is being indicated by this symbol y bar triple naught, right. In the case of one way and two-way, what you had? You had y bar or say y bar naught naught and so on. And similarly, if you try to see in the two-way analysis of variance, your alpha I hat was y bar I naught minus y bar naught naught. But now when you are trying to do it here, you have here one more factor here. So, you would like to have here say I double naught, and this y bar double naught will be replaced by y bar triple naught. And in case if you try to solve the normal equation, you will get here the estimate of here alpha I here as a like this y bar I double naught minus y bar triple naught, which is the mean of all the observation. So, this y bar I double naught will simply become here that you have to sum y I j k over the values of I, and you have to divide it by the total number of observation which are covered by the subscript j and k. So, that will become here j into k. And similarly, if you try to recall that you had obtained the estimate of beta j in case of two-way analysis of variance like as a y bar naught j minus y bar naught naught. Now, what are you going to do here? You are trying to add here one more subscript. So, beta hat j will become here y bar naught j naught, and this y bar will be replaced by say y bar triple naught like this. So, now if you try to see here, this beta hat j will come out to be y bar naught j naught minus y bar triple naught, and using the same definition that how you have defined this y bar I double naught, you can also define here y bar naught j naught by here summation over j y I j k and divided by the total number of observations which are covered by the subscript I and k. So, this will become here 1 upon I k. Now, similarly, you can obtain here the estimate of gamma I j as a gamma I j hat, and this estimate is being obtained that you try to solve this normal equation which is obtained after partially differentiating the error sum of square E, and then you put it equal to 0 and then you solve it, you will get here this estimate y bar I j naught minus y bar I double naught minus y bar naught j naught plus y bar triple naught. And now, here this new summation here y bar I j naught, this is defined as double summation over I and j on y I j k divided by the number of observation in the remaining subscript, this is here k. So, this becomes here 1 upon k. Now, if you try to observe here one thing, if you try to observe here the expression what you have given for here this alpha I, beta j and gamma I j. If you try to observe the structure that how you have obtained here, you have here mu I naught, you have here mu naught naught. So, when you are trying to obtain their estimators, you can see here you are getting y bar I naught, or say here in this case y bar I double naught. And similarly, in the case of beta j, you are getting here the estimate like here y bar here naught j naught. For here mu double naught, you are trying to get here y bar naught 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 triple naughts. So, if you try to see that there is a very systematic relationship between the parameters and their estimate, and that is helping us that without even solving the equation, we can directly write the estimator as long as we have the same setup and we are trying to use the principle of least square or method of maximum likelihood. And the same thing here is being done here also. If you try to see now in the gamma I j, we are trying to write down here mu I j by here y bar I j naught, this mu I naught, it is going to replace by mu I naught naught, mu naught j is going to be replaced by here mu naught j naught, and this here mu double naught, this is going to be replaced by here y triple naught. So, this is actually a great help in this algebra when we are trying to develop the analysis of variance test, and because of which once we have understood the basic fundamental, it is not that difficult to conduct the analysis and to write down the estimates of different parameters here what we have done here. And now you can verify here that the estimated what you have obtained for this gamma ij, and after solving the normal equation, that is a very much comfortable with the approach which you have just observed, and this can be can be obtained here directly also. But I am not saying that you have to do it like this, but I am again say clarify that the procedure here is that you try to differentiate this error sum of squares, try to put them equal to 0, try to solve them, and whatever the value comes you try to verify with the second order derivative whether those values are providing the minimum or the maximum values of E. But this is a sort of help which we are getting, but this help is being used here only after understanding the basic fundamentals, right. You should not jump to these things directly, otherwise you possibly may obtain the expression, but you will not be able to understand why you are getting such things. So, that is the point where you have to be very careful. Now, I have explained you that how I am going to obtain these expressions directly also, but then there is a very strong theory, strong algebra, mathematical derivation proof behind it, right. So, once you have obtained these least square estimators, then what you have to do? You have to substitute them in the this E, and you have to obtain here the SSE, that is sum of squares due to error or error sum of squares like this. You try to replace here mu alpha I beta j gamma I j in the error by this mu hat alpha I hat beta j hat and gamma I j hat. And if you simply try to substitute all these estimate what you have obtained here, you can obtain here simply here triple summation y I j k minus y bar I j naught whole square. So, this is your here sum of squares due to error in the case of two-way classification with interaction. And now you know that ultimately you are going to develop the test of hypothesis where you are going to use this SSE. So, I can write down here simply here that SSE divided by sigma square, that will follow a chi-square distribution with I j into k minus 1 degrees of freedom. Now, okay, so the first part of this analysis of variance is now completed. Now, we have to do the same analysis under H naught, that we assume that H naught alpha is true, H naught beta is true, and H naught gamma is true, and then we try to obtain their estimators, least square estimate, and then we try to find out their sum of squares due to error, and then we try to take the difference between the SSE that we have just obtained and the SSE that we are going to obtain under the respective hypothesis, and they will try to give us the values of sum of square due to A, B and interaction effect. So, now you have understood the entire approach, we simply have to implement it by doing the algebra. So, now I try to consider here the null hypothesis H naught alpha, where alpha 1, alpha 2, alpha I they are equal to 0, and we try to obtain the sum of squares due to error under this assumption, and we try to minimize it. So, under this case your model will become here y I j k is equal to mu plus alpha I, that will become 0 plus beta j plus gamma I j and plus epsilon I j k. Right. So, now we are trying to minimize the sum of squares due to epsilon I j's k under this model. So, now the approach is very simple, we are trying to indicate this sum of squares by here E 1. So, we have to now partially differentiate even with respect to mu, with respect to beta j and with respect to gamma ij. Then put it equal to 0, and then you can obtain the least square estimate of mu, beta j and gamma ij. So, now in this case, if you try to obtain here the estimator of mu, this will come out to be here mu hat like this one, y bar triple naught, right. And the estimator for beta j will come out to be here y bar naught j naught minus y bar triple naught, and the estimator of gamma ij will come out to be gamma ij naught equal to y bar ij naught minus y bar I double naught minus y bar naught j naught plus y bar triple naught. And one thing you can observe here, that these estimators what you have obtained here for mu, beta j and gamma ij, they are the same that you had obtained earlier in this case. If you try to see here this estimator of mu, beta hat j and gamma ij hat, they are exactly the same here what you have obtained here. So, now you can see here that you can save some time if you have understood how these expressions are obtained. Once again I will say I am not asking you to follow the shortcut, no shortcut allowed, because that will spoil your basic fundamentals. But since you already have understood that how these expressions are going to be solved, and this algebra is very simple, that is only a matter of some time factor that you may take 5 minutes, 10 more minutes, and I want to save them here, right. But on the other hand, I also want to show you the similarity between the expressions that you are going to obtain under different types of analysis of variance. So, you can see here that these expressions are the same that we had obtained earlier. So, that helps us a lot when we are trying to develop the analysis of variance under the higher order models, right. So, now what you have to do? Now, you have obtained these least square estimate, and then now you have to substitute them in the array sum of squares. So, we will try to substitute them in this expression, triple summation y I j k minus mu minus beta j minus gamma I j. We try to substitute these expressions over here. So, this is the and we try to obtain the minimum value of this expression, which will be obtained after substituting mu, beta j and gamma I j by their least square estimates. So, if you try to see here, this expression becomes here like this, and you simply try to substitute all the estimator that you have obtained here, and you try to square it. You will get here triple summation y I j k minus y bar I j naught whole square plus j k summation over I y bar I double naught minus y bar triple naught whole square, and all other your cross product term will become simply here 0, right. And this expression what you have obtained, this is actually the sum of squares due to H naught alpha, right. So, you can see here this first term is the simply the sum of squares due to error SSE that you had obtained earlier, and now this is the term here j k into summation over I y bar I double naught minus y bar triple naught. This will come here as such, right. So, you can see here this is the similar expression that you obtain in the case of two-way ANOVA also. Now, what are you going to do? If you try to take the difference between this expression and this SSE that you obtained earlier, right, you can obtain that this is the sum of squares due to the factor A, or it is something like when all the alpha 1, alpha 2, alpha I they are equal to 0, then this factor will become simply here 0. So, this factor is really trying to indicate that what will be the effect on the sum of squares due to error when there is a deviation from H naught alpha. So, that is actually the sum of squares due to the factor A, and this is obtained here as a sum of squares due to H naught alpha minus SAC, and this comes out to be here like this: j k summation over I y bar I double naught minus y bar triple naught whole square. So, that is the same thing that earlier you had written here the expression here E, and you had obtained the SSE by using all mu hat, alpha I hat, beta j hat and gamma I j hat. And now you have obtained here E1 and then you have obtained here SSE, but in this case the effect of alpha I is 0 and all other estimators are being used. So, if you try to take the difference between these two sum of squares due to error, that is sum of square due to error and sum of square due to error under H naught alpha, that is going to indicate the effect of the factor A in terms of sum of squares due to A. And after that we can very easily find that SSA upon sigma square follows a chi-square distribution with I minus 1 degrees of freedom. That is exactly on the same way as you did in the case of one-way analysis of variance, right. Now, you have to simply repeat the same exercise what you have just done. Now, you have to consider the second hypothesis H naught beta, beta 1 equal to beta 2 equal to beta j is equal to 0. Try to write down the model y I j k is equal to mu plus alpha I plus gamma I j plus epsilon I j k, and then try to minimize the sum of squares due to random errors epsilon I j k, and this sum is being indicated here by the term E2, right. So, if you simply try to partially differentiate E2 with respect to mu, alpha I and gamma I j, you get here the normal equations, you simply try to solve them and then you will get the estimators of mu, alpha I and gamma I j like this one, these. So, you can see here the estimator of mu here is simply y bar triple naught, the estimator of alpha I is y bar I double naught minus y bar triple naught, and the estimator of gamma I j here is y bar I j naught minus y bar I double naught minus y bar naught j naught plus y bar triple naught. So, once again you can see here that the form of the estimator in this case is fortunately coming out to be the same that you had obtained earlier in the first case, right. So, now you can see that the way you are trying to obtain these expressions, it is not very difficult, because once again what you will do, you will simply try to write down here this E2, you will partially differentiate with respect to mu, alpha I and say here gamma I j, put them equal to 0, solve them, and then you will get a very simple equation. You can very easily solve them and you are getting the same estimates. So, now you can be confident. Once you do this algebra yourself, you should be confident that you can write down these estimators now here directly. So, now you have obtained these least square estimator of mu, alpha I and gamma I j. What now you have to do next? You simply have to substitute these values in your sum of squares due to random errors, and then you have to obtain here the minimum error sum of squares. So, that can be obtained by simply substituting mu, alpha I and gamma I j by their estimators in the triple summation, say sum of square due to random errors. So, now if you simply try to substitute all these expressions here, just try to spend 1 minute or 2 minutes and try to simplify the algebra. This expression will come out to be like this: SSE plus I k summation over j y bar naught j naught minus y bar triple naught whole square, right. And you can see here, this is the sum of square due to deviation from H naught beta, or the sum of square due to effect B can be obtained from here. How? If you try to recall, you had obtained the E earlier, and from there you had obtained the SSE, which was based on here mu, alpha I, beta j and gamma ij. Then now you have obtained here E2, and then you have obtained here SSE, which is based on here mu, alpha I and gamma ij. So now in this case, if you try to take the difference of these two sum of squares due to errors, the difference is going to be indicated as if that is the effect of the factor b, and that is why we are calling it here as the sum of square due to b. So, this is simply sum of square due to h naught beta minus SSE, and this will come out to be here like this, which is the same expression what you have written here. Right, and then after that you can very easily write that SSB upon sigma square upon is following a chi-square distribution with j minus 1 degrees of freedom, exactly on the same lines using the same theorems and rules what you did in the case of one-way analysis of variance. Now, you are left with one more hypothesis. So, that h naught gamma, that all gamma ij's are equal to 0. So, now you have to do the same thing, exactly the same thing, but now you can very easily recognize what is this case going to be. Don't you think that when I am writing here the model here y I j k is equal to mu plus alpha I plus beta j plus gamma I j is going to be 0 plus epsilon I j k, don't you think that it is very much similar to your two-way analysis of variance model type of case? Yeah, that will help us if you try to observe it, means otherwise there is no problem if you cannot observe it. So, we simply have to write down this sum of square due to random errors, and then we have to partially differentiate it with respect to mu, alpha I and beta j, right. And then if you try to just partially differentiate them, put them equal to 0, you get the normal equations, and then you simply try to solve the normal equations, and then you get here the least square estimators of mu, alpha I and beta j here as like this. Mu hat comes out to be y bar triple naught, alpha I hat comes out to be y bar I double naught minus y bar triple naught, and beta hat j comes out to be y bar naught j naught minus y bar triple naught, right. And you can see once again that these are the same estimator that you have obtained earlier. So, now don't you think that you are now getting more confidence that how the similarity in the estimator is coming here? Now, you have to do the same thing, that you can obtain here the sum of squares due to h naught gamma, and from there you can obtain the sum of squares due to interaction effect. So, we try to obtain the minimum value of this sum of square due to random errors by substituting mu, alpha I and beta j by their least square estimate. So, we get here the sum of square due to h naught gamma here like this, and then if you try to simply substitute here the value of mu, alpha I and beta j as mu hat, alpha I hat and beta j hat, and if you simply try to solve them, just spend not more than 1 minute or 2 minutes, you can obtain here that this expression can be expressed as a sum of square due to error SSE plus k times double summation over I and j y bar I j naught minus y bar I double naught minus y bar naught j naught plus y bar triple naught whole square. So, now you have to do the same thing. Earlier you had obtained here the E, from there you had obtained the SSE. This was based on mu, alpha I, beta j, gamma I j. Now, you have obtained here say here E3, and then you are trying to obtain here SSE, but this is based only on mu, alpha I and beta j. So, if you try to take the difference of these two sums of squares, don't you think that they are going to indicate the effect of the interaction effect A B in terms of sum of squares? Right. So, the sum of squares due to interaction effect A B in this case can be obtained simply by here sum of squares due to h naught gamma minus SSE, and you can see here this term comes out to be here like this, which is the same expression here which you have obtained here. And yeah, using the same theorem about the quadratic form, you can also express this expression expression in the format of a quadratic form, and you can write down here very clearly that SSAB divided by sigma square follows a chi-square distribution with degrees of freedom I minus 1 into j minus 1. Right. Now, so now you have obtained the sum of squares due to the factor A, factor B, interaction effect AB, and sum of square due to error. And what was your basic objective? You wanted to conduct the test of hypothesis, in which you wanted to partition the total sum of squares into different orthogonal components, so that every orthogonal component is going to indicate the effect of a particular factor or particular effect, and all those sum of squares should be mutually orthogonal. Right. So, now the question here is this: you can very easily observe here that TSS, SSA, SSB or say SSAB, they are all here the quadratic form, including SSE. Right. And the way you have proved the independence of the quadratic forms using the theorem 7 and theorem 9 of the initial lectures, the same thing can be used here also. Right. And then you can very easily show here that this SSA, SSB, SSAB and SSE, they are going to be mutually independent of each other. So, once you have established the independence of these sums of squares, now you can construct here the F statistics. So, how we have done? Each of these sum of squares, their function is going to follow a chi-square distribution. So, now if you have two independent chi-square random variables, if you try to divide them by their respective degrees of freedom and take the ratios of sum of squares due to any factor and the sum of squares due to random error, then this will follow a F distribution. This is exactly what you have done in the case of one-way and two-way analysis of variance. The only thing was, in one way there was only one factor, so you had only one F statistics. In the case of two-way analysis of variance, you had two hypotheses, so you have two F statistics, one for alpha and one for beta. Now, in this case what will happen? That you have here two-way classification with interaction. So, you have here the factors say A, B and interaction effect A, B. So, you are going to have here three statistics, one for H naught alpha, one for H naught beta and one for H naught gamma, and they are going to follow an F distribution with respective degrees of freedom. So, what you have to understand here, what are you going to do here? Suppose if you try to take any factor here, say A, you try to write down its degrees of freedom and its a distribution. So, distribution is going to be based on say chi-square with certain degrees of freedom, right. So, for example, SSA upon sigma square will follow chi-square with I minus 1 degrees of freedom, and then you have to do the same thing for about this SSE upon sigma square, that will have some more some degree of freedom, say degree of freedom say E. So, and then you have to prove that both are going to be independent, and then based on that you can take the ratio say here like this upon sigma square upon SSE upon sigma square and try to divide by their degrees of freedom like is here, and then this will follow a F distribution. So, now you have to do this exercise 3 times, one for A and then for B using SSB and then for using SSAB. So, based on that you will have here these 3 statistics which are indicated by here F1, F2 and F3. So, F1 is the statistics which is used for testing the H naught alpha. So, this is here I j into k minus 1 divided by I minus 1 into SSA upon SSC. This follows F distribution with I minus 1 and I j k minus 1 degrees of freedom. And similarly, your here F2 is the statistic which is going to use to test the hypothesis H naught beta, and which is here I j into a minus 1 divided by j minus 1 into SSB upon SSC. This is going to follow a F distribution with j minus 1 and I j into a minus 1 degrees of freedom, and similarly your here F3 is being used for testing the hypothesis for H naught gamma. This is I j into k minus 1 divided by I minus 1 into j minus 1 SSAB upon SSE. This follows a F distribution with I minus 1 into j minus 1 and I j into k minus 1 degrees of freedom under H naught. So, these are all actually here the central F distribution, and if H naught alpha or H naught beta or H naught gamma are not true, then the corresponding F distribution will become non-central F distribution. So, based on that we can define here the decision rule that you try to reject H naught alpha, H naught beta or say H naught gamma if the corresponding value of F statistics which is obtained on the basis of given set of data is greater than their tabulated value which is obtained from the probabilities of F distribution at alpha level of significance, right. Now, you know how to take such calls without any problem, right. And then in case if H naught alpha or say H naught beta is rejected, then one can use the t-test or the multiple comparisons to find that which pairs of alpha i's or beta j's are significantly different, and the effects which are the got the same values or in which the hypothesis is getting accepted, they can be clubbed together in a single group, and the process of the multiple comparison test can be followed here without any problem, right. Now, if you think that what will happen if H naught gamma is not accepted, then one would not usually explore it further, right. And but if you say theoretically the t-test or multiple comparison tests can be used, right. So, and all these operations what you have done here, they can be combined in this analysis of variance table. So, now in this case you can see here the source of variation are here due to factor A, factor B and interaction AB, and their corresponding degrees of freedom here are I minus 1, j minus 1, and then due to interaction this is I minus 1 into j minus 1, and for error we have here I j into k minus 1, and the total here is obviously I j k minus 1. The corresponding sum of squares are SSA, SSB, SSAB and SSC, where SSC is going to be obtained by subtraction, for example say TSS minus SSA minus SSB minus SSAB, right, and finally TSS. So, because we are going to use here the Fisher-Cochran theorems, so that is why it is important for us that we try to obtain the SSE by subtraction, so that the Fisher-Cochran theorem holds, and we can use the property of additivity of the chi-square distribution and their corresponding degrees of freedom, right. And then you can obtain the mean squares due to A, B, AB and MSE, and if you try to take the ratio of MSA upon MSE, that will give you here the F stats F1. Similarly, if you try to take here MSB upon MSE, this will give you F2, and if you take that try to take the ratio of MSAB and MSE, this will try to give you the statistics F3. So, all these things can be combined in this single table. Now, after this, if you try to find out the expected value of these sums of square which you have obtained here, right. So, that you can obtain here without any problem. So, now we try to find out the expectation of different type of mean squares. Well, we already have found such a expectation earlier. So, the approach is going to be exactly the same what we have considered earlier. So, in case if you try to solve them, you can find here the expected value of mean square due to A, that is expected value of MSA as sigma square plus jk upon I minus 1 summation alpha I square. And you can see here that if your H naught alpha is suppose accepted, then all your alpha i's are going to be 0, and in this case this entire term will become simply equal to 0. And you can see here then it will be only here expected value of MSA is equal to sigma square. That means there is no effect of the factor A, and the entire variation is going to be explained only by the random errors epsilon ij's. So, this is how we are going to interpret it. So, this is the same interpretation which you have observed in the case of when you are trying to consider the null hypothesis. So, similarly, if you try to find out expected value of mean square due to B, MSB, this is again sigma square ik upon j minus 1 summation beta j square, and expected value of mean square due to AB, that is sigma square plus k upon I minus 1 into j minus 1 double summation gamma square ij, and most important, the expected value of MSE, that is mean square error, is coming out to be sigma square. That means an unbiased estimator of sigma square can be obtained by MSE. Right. So, now we come to an end to this lecture, and you can see here that in this lecture we have utilized the knowledge what we had gained in the one-way and two-way analysis of variance. And that is what I told you in the beginning, that if you are clear about those steps, that how you had obtained the different types of expression, test statistics, distribution in the case of one-way and two-way analysis of variance, you should be able to obtain those expressions here without any problem. But the difference is that now you will understand that why you are trying to do this algebra. It is not for only for the sake of mathematics, but there is a logic behind it, there is a rule behind it, there is a philosophy behind it, and there is an aim that we want to achieve something. That is why we are trying to do this algebra. If you understand, then there is no problem in understanding any of this analysis of variance in this world. Now, in case if I ask you that how to conduct the analysis of variance in a three-way model, that there are three effects which are affecting, or even I say that three-way effects with interaction, that means two effects at a time, three effects at a time, don't you think that is it very difficult? Certainly not. I am sure that if you have understood this one-way and two-way with and without interaction, extending these results and directly writing the ANOVA table should not be difficult for you in three-way, four-way, or whatever order you want. You simply have to understand how these expressions have been obtained and what is the similarity among those expressions. Well, I am not asking you once again, please remember, I am not asking you to do shortcuts, but I am simply trying to show you the similarity that will help you only. So, I would request you that you try to take it as a practice and try to write down the entire analysis of variance for three-way classification. That will be little bit lengthy, but not difficult, and that will give you enormous confidence that now after this you should be able to handle any type of analysis of variance in this subject. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.